In Lab 5, we will be looking at the physics and creating a Python model to simulate the motion of colliding pool balls in one dimension. The purpose of this lab is to observe and predict the motion of colliding pool balls and determine if the energy and momentum are conserved in the system. The process we will use Tracker to observe an example of this motion, video recording of this motion, and create a Python model that will simulate it and calculate the changes in energy and momentum over the time interval. So the results you're going to see are that momentum was not entirely conserved, as the collision was not entirely elastic, and kinetic energy was also not completely conserved. We'll touch a little more on what that means and how we found that later in the video. So the fundamental principles that we will be using: Newton's second law, pretty much the same way we've used it in every lab so far in order to update the velocity and position of the two particles, as well as the energy principle, which states that the change in the total energy in a system is equal to the sum of the energy changes in the system as well as the work done. This is going to be very important in creating the Python model, as it will allow us to determine the total energy in the system at any point in time, and thus whether any has been lost or gained into the system from the surroundings. The momentum principle, as it will be used in this context, will determine whether the momentum in the system has been lost or gained, as in a system that is not with no outside forces from the surroundings should have momentum completely conserved at all points of time. So let's take a look at the video we will be using for this lab. Here you can see it is a pool ball hitting another pool ball head on, and it is only causing motion in one direction. Let's see that. So then the one ball comes to rest and the 8 ball is sent down the table. So some initial conditions found from the tracker data includes the mass of the ball. The mass of the balls was recorded. The tracker initializations include the velocities, initial velocities, and initial positions of the balls. This was used. The initial velocities were found using the first few data points to determine the average velocity in the initial time constraint being observed. So some assumptions we're going to have to make for our Python model. We are not including the effect of air resistance on the balls or potential effect of the friction force on the balls from the table. We also are assuming that the contact causes a perfectly straight collision 180 degrees between the two balls. Otherwise, you'd have to account for the angle theta between the two of them. So initialization code, I'm not going to go through all of this and explain what every line is. You should know that by now. The mass, position, velocity, all of the initial characteristics of the system are initialized here, mostly as found through Tracker. So calculation loop, this is calculating for every value of time with a very small delta step for delta t prior to the collision, the new kinetic energy, the new momentum of each ball, as well as the new total kinetic energy and total momentum of the system. Alright, so then the post-collision calculation loop looks very similar. The new velocities that each ball has when initialized are slightly different, but the process of finding the kinetic energy and changes in kinetic and momentum are most. You can see here that when the code is run, the two balls collide, and just as it happened in the video, the motion of the balls as well as a few graphs are created. We're going to explain what all those mean, as well as the change in momentum and kinetic energy are calculated using Python. So what were those three weird graphs? First one was showing the kinetic energy of the two individual balls at all the points during the collision. As you can see, the collision happens at t equals 0.1, in which the kinetic energy of the 8 ball massively spikes upwards and the blue ball massively spikes downwards to almost 0. The total energy appears to stay effectively the same during the entire time, which would mean that the energy in the system was conserved. Here you can see it a little bit better. This is showing the change in kinetic energy of each ball as well as the total change in kinetic energy. The total change in kinetic energy is 0, and the two are opposite and proportional to each other. Okay, conservation of momentum, you'd see this graph looks almost identical. It's not. The only difference is the scaling but it acts in the same way where the change in momentum of the two balls act opposite of one another to create the change in momentum of the entire system to appear to remain at zero. Not quite though. Energy and momentum were not entirely conserved. As you could see in the Python shell window, that there was a small change in the total momentum of the system and the total kinetic energy of the system. So what does this mean though? What does it mean that the momentum and energy are not conserved? Energy loss from system is most likely through, say, thermal energy with the pool table, probably caused by the friction force. So that's energy being lost to the surroundings. And the loss of momentum was most likely due to an unaccounted for force, such as air resistance or friction force, causing the ball to slow down. The lower velocity in the later times would thus be a reduction in momentum. So the momentum was not conserved. So what if they did not collide exactly 180 degrees? The individual components of the momentum should theoretically still be conserved in their respective directions. However, you would then have to account for the different angles of collision. So that's it.